Hello, in this video, let's discuss a little bit about the capacitances in the MOSFET. So as we discussed, MOSCAP is a key component of the MOSFET. The source drains in the MOSFET are made up of reverse bias diodes. Now all these components are essentially capacitive. And so what ends up happening is most MOSFETs and in most MOSFET circuits, all nodes in these circuits tend to have a lot of capacitance in them, and hence that influences the speed of the circuit. So it's important to model the capacitances and see its impact on the performance. Now, what's capacitance? Now, capacitance kick in whenever we have sort of a charge storage present in the system. So if you look at the MOSCAP or the MOSFET in steady state, when there is a current flowing, it is associated with some charge stored in the depletion region and some charge stored in the inversion region. For example, let's look at the charge profile in the MOSFET here. So here I've considered a rudimentary MOSFET with a gate voltage applied, which causes an inversion layer to be formed. In addition to the inversion layer, we also have the ionized acceptors in the depletion region here. In the most generic case, let's assume that we have 4 terminals for the MOSFET and all the 4 terminals are biased. Right? So what you see is that there is a net charge present on the gate, and that compensates for the net charge present in the semiconductor. Also, in most cases, this is an NMOS, so in most cases when you're driving a current in this NMOS, the voltage at the drain is going to be higher than the voltage at the source, leading to this charge near the drain end in the depletion being higher than the charge at the source end. So generally when the MOSFET is conducting current, a bunch of charges are associated with every node, right? And so where does the capacitance come in? Now if I change the voltage at the drain slightly, there is going to be a change in the stored capacitance. So this measure of change in capacitance as a function of a change in voltage is essentially modeled as the capacitance associated with that node. So let's look at those 3 cases. So we look at 3 cases, especially when we deal with MOSFETs. The first case is when, let's look at the 3 cases for the capacitance. The first case is what happens when the source voltage wiggles. Second case is when the drain voltage wiggles, and the third case is when the substrate bias wiggles. So when we apply a small change to the voltage at the source, it ends up changing the profile of the charge in the semiconductor, and it also ends up therefore changing the amount of charge present in the gate. So you have a change in the gate charge and a change in the semiconductor charge, both of which can be modeled as the CGS, or the capacitance between the gate and source, and CBS, which is the capacitance between the substrate and the source. In the next case, suppose I want to see how a voltage change in the drain voltage affects the charges. What you see is similar to the source. When I apply a change in the drain voltage, that change is associated with a change in the total charge present in the semiconductor. So what this would do is that would change the depletion profile near the drain end of the channel. This increased charge will essentially also show up as a change of charge in the gate. Right? So again, when the drain wiggles, you're going to have a capacitance associated between the gate and drain, and a capacitance associated between the substrate and the drain. Now the third capacitance occurs when I wiggle the substrate and keep the other two constant. So now when I wiggle the substrate here, that is associated with a change in the depletion region in this fashion. So it impacts again both the charge only in the substrate and the charge in the gate. And so therefore here we see that there is a CGB that is associated with this structure. So please note that we don't specifically call out a change in the gate voltage, because these have been individually modeled as CGS, CGD and CGB. So by including these terms, you've already included what happens to the structure suppose the voltage on the gate wiggles. So part of it is shared with the source, part of it is shared with the drain, and part of it is shared with the substrate. So CGS, CGD, and CGB represent the effect of the gate on one of the terminals of the transistor. And these caps are essentially sometimes referred to as looking into the gate of the transistor. One thing to keep in mind is all these capacitances are bias dependent, right? Which means that, and that's because they depend on the region of operation of the transistor. Suppose I had not created an inversion channel, then the capacitance numbers or the way the various nodes would have interacted would have been much different than when a channel was created. And so therefore always remember that when you look at the capacitance of the MOS structure, in reality that capacitance is going to be bias dependent. So if you want to do an accurate job, you need to develop a model that includes this bias dependence. So generally a very few closed form expressions are available for quick analysis. So we look at a few very simple back of the envelope formulae that we can use to quickly understand what might happen in the structure. Another thing to keep in mind is that all these models that we are doing are valid only for a maximum frequency, right? Basically, remember that semiconductors have majority carriers, minority carriers. These carriers are associated with their time constants. So in general, response of a semiconductor device to a oscillating frequency is frequency dependent. And as you go to higher and higher frequencies, there are a lot more parameters that need to be taken into consideration. So this model again is mostly valid for low to mid frequencies, and it fails at very high frequencies. At high frequencies, we use what is known as the Y parameter model for the MOSFET. So now let's look at the individual regions and see what happens to the various capacitances. Now let's first look at the linear region. So what is the linear region? The linear region is when I've created an inversion layer, but I've applied a very small bias between the drain and source. So now if I apply additional voltage at the drain or the source, all that will do is it will create a linear drop in the inversion region. So that additional capacitance or that additional charge is going to just appear on both sides of the source and drain. So what happens therefore is we see that when you a MOSFET in the linear region and when you apply voltage at the source drain, you essentially end up getting an average capacitance of Cox by 2 from the source to the gate and from the drain to the gate. The capacitance across the PN junctions are related to the VT change due to VB. Right? So we can write CGS and CGD as just Cox by 2. Now this is because the inversion layer is constant and we assume in linear region that the inversion layer doesn't have a huge change as it go from the source towards the drain. Right? The charge density we assume to be roughly constant. And if you look at the substrate component, if you look at CBS and CBD, CBS and CBD are given by some part of this capacitance, and that part is dictated by how much the VT shifts as a function of this bias that you applied between the source and substrate. CGB, which is the capacitance between the gate and the substrate, is 0 because you have a continuous inversion channel that is screening the gate from the substrate node. Now let's look at the other extreme when the MOSFET is pushed into saturation. Now when you push the MOSFET into saturation, the channel is pinched off, which means the drain end of the channel is not under gate control. So if you were to think about the inversion channel, if this is your source, this is your drain, your inversion channel looks something like this, right? That is, there's a lot of charge present at the source side, and at the drain side the channel is pinched off. And so CGS is calculated along the length of the channel. Now as I wiggle the source more, there is going to be closer coupling between the gate and source than there is between the gate and drain. In fact, there is no coupling between the gate and drain because at this point when pinch off has occurred, the gate and drain are essentially independent of each other. So what you see is that there is a coupling between the gate and source. However, because of the nature of the charge, that the charge increases here and essentially falls down to 0, the coupled charge is actually less than what would have happened suppose this was a parallel plate capacitor. So therefore what we see is that we expect CGS to be some value as a function of Cox, We expect CGD to be 0, but we also expect CGS to not be Cox but to be some value less than Cox. And the reason is because the charge is not uniform across the entire gate, but rather biased closer towards the source. And because of the fact that you now have this drain and gate cutoff, the body or the substrate and the gate can now talk to each other. So the gate is not insulated from the substrate, so you end up seeing a CGB associated with the transistor in saturation. So very simply, to first order, we treat CGS. So in saturation, we treat the gate to source capacitance to be roughly 65% of Cox or 2/3 Cox. CGD, because the channel is pinched off, the gate and drain are isolated, so CGD is 0. CBS is again given by this component of CGS modulated by the change of VT because of the substrate bias, and CBD again is 0. So what you see is that there exists a capacitance in saturation between the gate and source and the substrate and source. For most practical applications, the drain is essentially isolated from the gate and the substrate. And CGB, as I told you, because of the fact that you have this pinch off, a CGB exists between the gate and the substrate, and it is given again by this expression. Please remember, all this is happening because of the fact that the VT of the transistor is changing because of a bias between the source and substrate. If this term was small, essentially you would find CGB to be very small. So now let's put all this together and see how does the capacitance at the various nodes change as a function of VDS. So if I'm going to plot C as a function of VDS, let's first mark out which is the saturation region. So this is the region of saturation at higher VDS. So in this region, the MOSFET is going to be either in very close here, it's going to be linear, and further on it's going to go into triode region. So what we see here is CGS. If you look at CGS, which is one of the main capacitors in the structure, CGS in the linear region starts off at half Cox and it increases to 2/3 Cox by the time it hits saturation. So in saturation, for the most part, we treat CGS to be constant. CGD, on the other hand, is valid only in the linear and triode region, because as the charge profile changes and as the charge profile becomes increasingly independent at the drain, your CGD drops to 0. So we say that once the transistor is in saturation, the gate and drain do not talk to each other. Now CBS is going to be a linear function of CGS, and it's given by the dVt by dBsp. So CBS looks very similar to CGS and is generally much smaller. So in many cases we also tend to ignore this for if dVt by dBsp is very small. Similarly, CBD is a linearized version of CGD and again is a small quantity. And finally, the gate to substrate capacitance only kicks in saturation. So we see that gate to substrate is essentially shielded by the inversion channel, by the continuous inversion channel in the linear and the triode region, and by the time it hits saturation, it achieves a small value. So again, for many of our applications, especially when you do circuit design, we tend to neglect these three capacitances, and we'll mostly worry ourselves with CGS and CGD because those tend to be the larger capacitors in the structure. One note to think about the capacitance of the source drain. So if I just look at the cartoon of the MOSFET, right? What we are looking at essentially here so far have been the capacitances from the source and drain in what's happening under the gate. So it's the capacitance to the depletion region, it's the capacitance to the inversion channel, etc. But remember that there is this additional reverse bias. So if you look at the source and substrate, you have this diode here. And similarly between the drain and substrate, you have this diode. And so both these diodes are in reverse bias, and this has a substantial area associated. So what we see here is that these two regions also contribute to the capacitance at this node, and that capacitance is layout dependent because it depends on the width of the source drain and it depends on the junction depth of the source drain. The reverse bias diode, what we know is that this capacitance, the capacitance of the structure in reverse bias, is given by epsilon S divided by W into A, right? And so this W is bias dependent, right? This is the depletion width. This W here is the depletion width. And so this depletion width is bias dependent, which means that this capacitance also has a bias dependent component. So again, when you're looking at MOSFET circuits and when looking at the various nodes, one thing to keep in mind is that almost all capacitors in MOSFET circuits tend to have bias dependence. So do an accurate analysis for timing or speeds, you have to include those when you're doing the simulations. In addition to all these, you also have other extrinsic parameters. So typically, let's look at the cross section of a MOSFET. So this is the top view of the MOSFET and this is the side view of the MOSFET. So we have the source and drain and we have the gate. Normally what happens in self-aligned MOSFETs, we have an overlap between the source drain and the gate, and that is called out sometimes as the L overlap, right? So in reality, the electrical gate length of the transistor tends to be smaller than the poly or the gate length, physical gate length of the transistor. Additionally, we also have a finite height to the gate and an oxide thickness. So when you look at the source drain a little bit in detail, in addition to this capacitance which we looked at in the previous slide, we have a capacitance which occurs due to this overlap, because this looks like a parallel plate capacitor. So we have a capacitance between this overlap between the gate and the source drain. Additionally, we have a metal and a semiconductor placed close together. So there are what are known as fringing fields present in the structure. So there exists a capacitance between this wall of the gate and this region of the semiconductor. So now if I assume that the semiconductor grows beyond the surface, then this capacitance will increase, right? So this fringing capacitance actually becomes very critical, especially if you look at current FinFETs and GAA structures. So it's the fringing capacitance which dominates the capacitance at the gate. And this is something which is process dependent. It's not necessarily dependent on what's happening in the MOSFET. It's related to how you build the MOSFET. A similar version of the fringing also occurs because of the fact that you have some capacitance that can happen because of fields which originate from the top of the gate and terminate onto the source drain. So we model the overlap capacitance as a linear parallel plate capacitor, and we model these two fringing capacitances based on the angle between the two planes using basic electrostatics. But what we'll see is very simply in most simulators, because all these are so much layout dependent, and because of the fact that we are limited in the quality of our models, we sometimes use empirical models which say that the gate to source capacitance or the gate to drain capacitance is a function of the width of the transistor. Remember, this transistor is uniform into the plane of the video. And so we talk about a fitting parameter, which is the CO double prime. And we say that this capacitance is width times the CO double prime. Because then this gives me a handle as to what happens if I change the width of the transistor, which is basically what a designer has to do when he's designing circuits. So this CO double prime is known as a cap per unit width and generally used in all models. So to conclude, modeling of capacitance is very important. Modeling of the capacitance is structure dependent, is bias dependent. Typically, these models are not closed form expressions. Most of these capacitances are bias dependent. So if you want to do an accurate model of the speed of the circuit, and this speed depends on all the various capacitances present in the nodes, it's important to do an accurate modeling of the capacitor, and that requires simulators. However, what we have seen in this video is there are a few corner cases in which we can look at closed form expressions so that they give us some idea when we begin to design circuits.